Hello everyone, welcome back to another physics lesson. I'm Physics Michael, and in this video we are going to explore an exciting and fundamental topic, describing waves. We will cover what waves are and introduce key terms like displacement, amplitude, period, frequency, wavelength, and phase difference. These are the building blocks for understanding all types of waves behavior. So let's get started. Waves are everywhere in our world. Think about water waves in the ocean, sound waves coming from a speaker, seismic waves from earthquakes, microwaves used in a microwave oven, radio waves for TV signals, and waves on a string. Today, we will focus on a wave on a string to help us understand how to describe waves using different physical quantities. First, let's start with what are waves. Waves are periodic disturbances traveling through a space caused by vibration, as shown in the animation of wave on a string. We can see that the particles along the string are initially rest at its undisturbed position or equilibrium position. Then, once the vibrator starts to vibrate, the wave's pattern moves along the string, so does the energy transfer. However, if we focus on a single particle on the string, it just oscillates up and down around its equilibrium position, meaning that the particles are not traveling along the string. This shows us that waves can transfer energy from one place to another without transferring the materials. Then let's start describing waves using two important quantities, displacement and amplitude. In the context of waves, displacement is the distance of a particle on a wave from its equilibrium position or undisturbed position as shown in the figure. Different particles each have a displacement up or down from its own equilibrium position. So displacement can be positive or negative depending on the direction. And for these points, they are at the maximum displacement, which is called amplitude. We can use the height of the peak or depth of the trough from the equilibrium line to find the amplitude. Amplitude tells us how strong or intense the wave is, indicating that greater amplitude means more energy is being carried by the wave. Next, let's talk about period and frequency. But first, we need to understand what is meant by one cycle or one complete oscillation. As shown in the animation, the green particle is oscillating up and down about its equilibrium position O. The highest position of its oscillation is point A, and the lowest position of its oscillation is point B. One cycle or one complete oscillation is the whole journey of the particle, starts from one point and ends back to the same point, moving in the same direction. For example, starting from O, it moves upwards to A, then downwards from A to O, continues downwards from O to B, and finally upwards from B back to O. This OAOBO journey is called one cycle. And similarly, the AOBOA journey is also called one cycle. And if the particle follows the BOAOB path, it is still called one cycle. So now we can define the period. The period is the time taken for one complete oscillation of a point in a wave. Using a displacement time graph for the oscillation particle, we can easily find that the time taken for cycle OAOBO, this is a period, and the time taken for cycle AOBOA, this is a period as well. And similarly, the time taken for cycle BOAOB is still called a period. And then the frequency f is the number of complete oscillations per unit time of a point in a wave. Frequency and period are inverses of each other. That means f equals 1 over t, and it is measured in per second or hertz. 1 hertz means one complete oscillation per second. For example, if a wave has a period of 0.2 seconds, that means it has 5 complete vibrations in 1 second, so its frequency is 5 per second or 5 hertz. Now let's move on to wavelengths. Wavelength, usually represented by the great letter lambda, is the distance between two corresponding points on a wave. which are oscillating in step with each other. That means they are always moving in the same direction at the same time, like crest to crest or trough to trough. Wavelength tells us how long the wave travels in one full cycle. As shown in the animation, once the green particle completes one cycle, the wave travels the distance to the other green particle along the string. And if we focus on the subsequent movement of the two particles, we find that they are just vibrating in step with each other. So the distance between the two particles is called one wavelength. Similarly, these 2 points are vibrating in step with each other, so their separation along the string is one wavelength as well. And these 2 points are also vibrating in step with each other, so this is still one wavelength. Commonly, we can find the wavelength by the distance between two adjacent peaks, or distance between two adjacent troughs, just as shown in figure. Another important idea is phase difference. This describes how much one particle is leading or lagging the other particle in the wave, expressed in either degree or radians. Just as shown in the animation, starting from point A, the wave propagates to the right along the string, but particles on the right lag the particles on the left, and once the particle at A completes one cycle, the wave travels one wavelength to particle at D, and the particle at D is just starting to vibrate. This means the particle at D lags behind A by one cycle or by one wavelength. Hence, let's relate one cycle or one wavelength to 360 degrees or 2 pi, because one cycle is just like completing one revolution around a circle. Then we can say that point D lags point A by 360 degrees or 2 pi. We can say the phase difference between A and D is 360 degrees or 2 pi. And if we focus on the subsequent motion of A and D, we can find that the two particles are oscillating in step with each other, so we can say they are in phase. In addition, let's focus on the point B and D here. They are half a wavelength apart, which means D lags B by a half cycle, so they have a phase difference of 180 degrees or pi. And they are always moving in the opposite direction at the same time, so we can say they are completely out of phase or antiphase. And for points C and D, we can say that D lags C or C leads D by a quarter of a cycle, so the phase difference is 90 degrees or 1/2 pi. Obviously, they are not in phase. So phase difference can be calculated by the fraction of a cycle times the degree of one cycle. Or we can just use equations delta phi equals the x divided by the lambda times 360 degrees or 2 pi. Let's bring everything together with a simple example. We are given a wave profile on a string at a particular moment. We want to find the displacement of points A, B, C, D, and E, and figure out the wave's amplitude. Just as shown in the figure, we can use lines with arrows to indicate the displacement of each particle. A is 1 cm below its equilibrium position, so XA is negative 1 cm at this moment. Similarly, XB is negative 1.7 cm, and C is at the equilibrium position, so no displacement. Then point D is 0.8 cm above its equilibrium position, so XD is positive 0.8 cm. Similarly, XE is positive 1.7 cm. And the maximum displacement of the wave is 1.7 cm, so the amplitude is 1.7 cm. Then, if a particle on the wave finishes 20 complete vibrations in 10 seconds, let's find the wave's period and frequency. The period is time taken for one cycle, so we take 10 seconds divided by 20 cycles. That gives us 0.5 seconds for the period. And for the frequency, we do the inverse of period. 1 divided by 0.5 equals 2 per second or 2 Hz. That means the wave completes 2 full cycles every second. Next, let's find the wavelength and obtain the phase difference between BC, BE, EG, and AC. For wavelengths, let's use the distance between two adjacent peaks or between two adjacent troughs. As shown in the diagram, we can read the wavelength is 2.5 centimeters. And since difference between BC is a quarter of wavelength or a quarter of cycle, so the phase difference between BC is 90 degrees or 1/2 pi. And the difference between BE is 1/2 wavelength or 1/2 cycle, so the phase difference between BE is 180 degrees or pi. We can say B and E are antiphase. And difference between EG is 1 wavelength or 1 cycle, so the phase difference between EG is 360 degrees or 2 pi. We can say E and G are in phase. For A and C, the distance between them is 1 centimeter. We can find the fraction of a cycle by the ratio of AC to 1 wavelength and use the fraction times the degree of 1 cycle. The fraction is 1 over 2.5 and times 360 degrees. The phase difference is 144 degrees or 4/5 pi. Let's summarize what we've learned today. Waves are periodic disturbances traveling through a space caused by vibration. Waves can transfer energy without transferring the materials. To describe a wave, we can use the quantities below. Displacement is the distance of a particle on a wave from its equatorial position, and amplitude is the maximum displacement. Period is the time taken for one completed vibration of a particle on a wave, and frequency is the number of completed oscillations per unit time of a particle on a wave. Wavelength is the distance traveled by a wave in one completed vibration, and the phase difference is the fraction of a cycle of one point leads or lags the other, expressed in either degrees or radians. And if phase difference between two particles are 360 degrees or 2 pi, they are in phase, which means they are oscillating in step with each other. And if phase difference between two particles are 180 degrees or pi, they are antiphase, which means they are always oscillating in opposite direction with each other at the same time. That's it for today's video. Thanks for watching. I hope you have a better understanding of how to describe waves in physics. And don't forget to apply these concepts when you observe waves in your everyday life. I'm Physics Michael, and I will see you in the next video.